Kirchoff's Rule Lightbulb Lab by Alan, Eduardo, and Ali. We want to use Kirchoff's law stating that the amount of current entering a junction is equal to the amount of current exiting a junction. First, we'll measure the voltage and current, then compare the experimental current to the theoretical after finding and writing 6 independent equations. The resistance is found by dividing the voltage by the current, and we'll compare those as well to the color code resistors used. The junction rule, or Kirchhoff's current law, deals with currents at a single node. A node is a place where 3 or more elements join together. The sum of the current flowing into any junction should be equal to the current to the sum of current flowing out of the junction. This is a result of the conservation of charge. The loop rule, also called Kirchhoff's law voltage laws, deals with voltages around a closed loop. A closed loop is any path through circuit element where it returns to where it started without passing through any elements more than once. It states that the sum of the voltages rises because of the battery around a closed loop is equal to the sum of the voltage drop caused by the resistors around a closed loop. This is due to the conservation of energy. The amount of current split into the circuit should equal the amount of current coming out of it. The amount of voltage and current should stay the same across each of them, and we hypothesize that the batteries connected to the switch and light bulb will then cause the light bulb to turn on. These are the formulas that we will use to measure the junction rule, which has to deal with the current, the loop rule, which deals with voltages, and resistance, which we find by taking the voltage and dividing it by the current. We will use Pascal circuit plate, and we will have 3 loops shown as the boxes in this drawing made by Alan, and the current will come out of the battery through the switch and through each of these 5 resistors. We have a junction where we have 3 of the resistors coming in on this first line, and we will have the current connected to the 3 light bulbs at the end when all the current has passed through the plate, and we will see if they turn on.
Here are the materials that we're going to use to set up our circuit. So first, what we have here is the Pasco circuit board, and then you're going to need 2 batteries, as well as 3 small light bulbs. You're going to need 4 resistors. 3 of them have to be 560 and then 1 1000 resistor. You're also going to need a couple of wires. Here we have 3 pretty long ones, 3 medium ones, and then 1 very short wire. And lastly, you're going to need a voltmeter to measure the voltage and current on your circuit.
Here is the setup for the Kirchhoff's circuit plate board. We have a total of 3 loops. We have the batteries are connected to this wire, which will push a current to the first resistor. This one's 560. And then we have another wire coming in through the second resistor. This is 27 ohms coming down. And here we have the third resistor, the fourth one. These are both 560 ohms. And the 5th resistor is 1000 ohms. We have a current going through each of the resistors coming back to the battery, And now we will attach a wire at the end of the circuit after passing all the resistors to the light switch and the light bulb. And the light bulb did not turn on.
So when we pushed the button, the light didn't turn on. And the reason for this is because there's not enough current reaching the light bulb right now. And on this board, we have 3 different loops. And then we also have too much resistance with these resistors right here. So in order for the light to turn on, we're gonna have to decrease the amount of loops and decrease the resistance amount.
So with the previous circuit, when we turned on the switch, the light bulb did not light or turn on. And what we did is that we figured out that there was too much resistance, so we switched the resistors to be 10 ohms, and we took out 1 loop and also this resistor, which is 27 ohms. And when we now turn on the light switch, it does turn on, but it's very dim. So we figured that because it's very dim, the second and the third light will also not turn on. So we will figure out a way to add less resistance and take out also 1 loop. For this new setup, we only have 1 loop coming in from the switch, going around with 2 resistors, and coming to the end, we have the wire connecting up to the light bulbs, and then these light bulbs are connected back to the battery. But we took out the 2 resistors that we had, and now when we turn on the light, only the first one still turns on. Even though we thought that by connecting the wires, that they would all be turned on because the current would flow through them. But we realized that each of these are in parallel, so each of them have to have a wire connected to the source.
So now we're gonna measure the voltage, and we can see that that is registering correctly. And then now we're gonna try the current. And now we can see that our current is actually too small. And we'll address that later in the video. Now we're going to show how to measure the theoretical resistance. So connect these 2 together. And we can see our resistance is about 1.4.
So for this final setup, we have still 1 loop with the 2 resistors, but now we have individual wires connecting to each of the batteries to the source of the power. So now when we turn on the light, we can see that it works and all 3 light bulbs turn on. And now we're going to measure the current to make sure that it does work. And we can see that we do get a 2.4 current, which is what we wanted.
Okay, so here I'm going to present our findings for our data and our results. So first, here in this section, we have the data recorded, including our measured voltages and measured currents. Those 2 values helped us find our theoretical current that we eventually plugged into our 6 independent equations. And down here is what we ended up with for our theoretical currents. And then we compared that to our experimental currents, which was from this column right here, and got a percent error for each one. Some are significantly high and the other ones were very low. This probably would have been because of certain errors in measuring, but this is what we ended up with for that. Now with the second part we did with the light bulbs is that we also measured the voltage and the current according to Kirchoff's law, and that the amount of voltage and current going in should equal to the one voltage and current going out. And from there, we also found our experimental resistance as well by simply dividing our voltage by our current and got each resistance from our 3 light bulbs. And then we ended up with a set of percent errors for that one. Those weren't as high or super low compared to the percent errors from the first one down here, but this is what we also end up with. So in conclusion, our percent errors basically ranged from being high in the currents, but being fairly within the middle range for our experimental resistance. So our data could have reflected possible random errors that were caused, whether it's due to measurements of our voltage and current or other possibilities.